Okay, so we're going to be taking TNOTES today on vectors and scalars, and you might notice a few different things is that when the screen changes to a new slide, you're going to see everything on there. So just go ahead and pause the video, take the notes, and then listen to the explanation of the notes. Sometimes I will be putting things up step by step. However, other times if it is just all up, go ahead and pause it and start the video back up when you're finished taking the notes. So vectors and scalars. Vectors are pretty much arrows. It is a quantity with a direction, so the arrow points in the direction that the object is moving towards. It also gives magnitude, so the size. So it's shown as bold italic, such as F for force will be a bold italic F. Examples of vectors, which are just pretty much quantities, right? They're displacement, velocity, acceleration, momentum, force. These are just a few examples. There are many more. So, for example, if you're looking at a car that's driving, it's going 30 meters per second north. So remember, it has the magnitude 30 meters per second. North is the direction. Plane flying 400 miles per hour is the magnitude, and then south is the direction. So this is a vector quantity. For scalar quantities, there is no arrow. It is just a quantity with only the magnitude. So it's shown as a normal italic lowercase. For example, mass, length, time, volume, speed, density, temperature, pressure, and again, there are many more quantities that are scalar, but pretty much all you have to know is it's just a quantity. It does not give a direction. So for example, a car driving 30 meters per second. A plane flying 400 miles per hour. 1 kilogram is how much the book weighs. So these are all quantities that are scalar. They do not give direction. Net force, also known as a resultant. So whenever you're combining all the forces, sometimes you add them, sometimes you subtract them. All these forces that are acting on an object is called a net force. Vector, in the same direction. So if you have vectors, quantities that are going in the same direction, all you have to do is add them. So for example, you have an object that is either being pulled or pushed at 10 newtons, and there are two sets of 10 newtons. So your total would be 20 newtons, and that would be the net force that is acting on that object. Here's another example where you have two arrows denoting the direction of the force, and it is going 8 kilometers and 8 kilometers east, and so your resultant would be a total of addition, so it would be 14 kilometers east. When vectors are going in opposite directions, all you need to do is subtract the quantities. So for example, if you have applied forces 10 newtons to the right, 5 newtons to the left, or in opposite directions, then your net force would be the subtraction of those two quantities. Therefore, your object would have a plus 5 newtons to the right. That would mean that this object would move to the right, 5 newtons. Cool? Okay, so the next one is 8 kilometers, and we have 6 kilometers going against the object. And so therefore we have a resultant of 2 kilometers east. Remember, this is a vector, so it has both direction and magnitude. Okay, here are 3 examples of boxes being pulled or pushed in different directions. And what you need to do is find out what the net force is. Okay, so for this first one over here, we have a box showing that there is an action of force being put on this box to the left of 10 newtons, and then the same amount of force of 10 newtons to the right. The net force then would be 0 newtons because these two arrows are in opposition, therefore they would subtract from each other and you would have 0 newtons and the box would be standing still. For the second box down here, we have 2 pairs of 10 newtons going in the same direction. So here's where you will have 2 vectors adding to get an answer of 20 newtons to the right. And notice here that the magnitude, the size of the arrow for the 10 newtons is half the size of the total of the resultant force in the answer over here. For the bottom problem, we have 10 newtons to the left and 8 newtons to the right. And notice that the arrow of 8 is a little bit smaller than that of the 10 newtons to the left, and that is because you need to make sure that the lengths of the arrows are correct in comparison to each other. The answer to this, obviously these are going in opposite directions, you need to subtract these vectors, and then you know that the box will be moving to the left 2 newtons. Over here, notice that the forces are going up and down. So forces are not only left and right, forces can be up and down. Forces can also be at diagonals or at different angles, even in 3 dimensions. So let's go ahead and look at this. So this is showing, let me find my cursor, this is showing that the tension, the force of tension is pulling up 1200 newtons, whereas gravity is pulling down 800 newtons. So it's still going in opposite directions. So therefore, if the forces are going opposite directions, then all you need to do is subtract, and your answer is 400 newtons, and the object would be going up. Okay, so try this next one, and you should have the answer of 200 newtons down. So you would have more force pulling down from gravity. The net force on the third object, which shows that you have the normal force or surface force, 50 newtons, gravity 50 newtons, and to the left you have friction 20 newtons. It is going to be 20 newtons to the left. When adding vectors in one dimension, the first step would be to draw the diagram with vectors tail to head. So for example, if you had a problem where you have 2 sets of 10 newtons moving the object to the right, and we name this arrow G and arrow H. When you draw the diagram with vectors tail to head, you would get the arrow G added on to arrow H. The second step would be to draw a final line that is the length of both added vectors. And what we know is that when you add G and H, you would get the resultant. And in this case, because the arrows are both moving in the same direction, you would add them. Your resultant would then look like this. And there are 2 arrows on the resultant, which then just shows that you understand that this was the sum of 2 vectors that were being resolved. The third step would be then to determine the magnitude. Again, remember that arrow G and H equals the resultant. If you were to add in the numbers, we have 10 newtons plus 10 newtons equals 20 newtons. To determine the direction, all you would need to know is that if the movement of the arrows are to the right, then your value would be positive. If the forces were moving to the left, then the values would be negative. In this case, both of the arrows were moving to the right. Therefore, we have the magnitude of 20 newtons. The direction is to the right. When adding vectors that have right angles, there are 2 different approaches. The first approach is a tip-to-tail approach. Step 1 is to draw the diagram with the 2 vectors with one tip touching the tail of the other arrow. Over here we have an example of an object moving 5 newtons north and 12 newtons west. Here we have the tip of one arrow and the tail of the second arrow. Step 2 is then to draw a line that is from this point to this point. So it would look like this. You would connect the tail end over here to the tip of the other arrow, and this would be your resultant. Notice how we drew 2 arrows here to show that this would then be the sum of both the north and the west vectors. Step 3 would then be simply to use the Pythagorean Theorem to find the resultant vector. So in order to find the value, all we would need to know, and remember this comes from our math, that we can say a squared plus b squared equals c squared. So we know our a, we know our b, we can find our c. When we plug all that in, we get r squared, which is the resultant, so that's our c squared, equals 5 squared plus 12 squared. When you solve for this, you get r squared equals 169, and then when you take the square root of r squared, you get 13 newtons. Now, the second approach is called the parallelogram method. And with step 1, you again draw the diagram, but you do it this time with both the tails of both vectors touching. The second part is to project both vectors across to form a parallelogram, or a rectangle. So it would look like this. Then, at this point, you're going to draw a diagonal from the tails, which is right here, where the intersection of the tails of the two vectors are, to the corner point. So you should have this. This is your resultant, and this is the angle right here that it makes with the resultant. Step 4 would then be to use the Pythagorean Theorem, just as we did in the tip-to-tail method. And remember, that is a squared plus b squared equals c squared. When we substitute the numbers in for the a and b variables, we get the same exact answer, r equals 13 newtons. The fourth step would then be to use trigonometry to find the direction of the resultant. Now, remember that the resultant is the blue line right here. We have found that value to be 13 newtons. We were given 5 newtons north for one vector and 12 newtons west for the other vector. And when you made your parallelogram, remember, just using the knowledge of trigonometry, is that this is the same magnitude as the 12 northwest vector down here. Likewise, the 5 newtons north vector here is the same as on the other side. It's just a mirror image. Using this information, we can then solve for theta. So if we were to use tangent, remember we're going to say tangent of theta equals, and that's the opposite over adjacent, so that would be 5 newtons divided by 12 newtons. Then we take the arctangent, so we move that tangent over, and when we solve for theta, we get an answer of 22.6 degrees. Now, when you're subtracting vectors, you might be asking, when do we see this? When do we need to use this? When is this relevant? So whenever you're talking about velocity and you're talking about the change of displacement, you're actually looking at your figure in the final, so what distance you finished minus the initial. So your final minus the initial, this is when you would be subtracting your vectors, and this is all over time. Another one is with acceleration, again, the same thing, your velocity final minus your initial velocity all over time. And then the famous force equals mass times acceleration, and this is if it were a constant mass. Now this is multiplication, but a more general equation would be where force is changing in momentum by the change in time, which would then be your change in p, which is again your final momentum minus your initial momentum all over the change in time, so your duration of time. So these are some of the most common equations that we use in order to subtract vectors. Let's review how to subtract vectors in one dimension. So here we have a situation where a car is initially going 10 meters per second. And then in the second scenario, the velocity of the car is now 40 meters per second. We want to know what the difference is. So in this case, you need to first write the vector equation. And so what that looks like is velocity equals, remember, final minus the initial velocity. So that's why it says that velocity equals b minus a. And notice here that the arrows are going in the direction that the car is going, so in the positive direction. So now that we're trying to draw a vector addition diagram, what we know is that this negative actually flips the arrow the other way. So if you showed here your arrow, your vector of scenario B going to the right, then your A would be opposite than that. So therefore, your arrow for A would be pointing to the left. Your resultant, therefore, would then be a shorter vector overall, but also showing, again, remember the two arrows to show that you know that this is resolving two vectors. And so this is the change in velocity, and this right here, the blue arrow, will be your resultant. So what we're showing here is that the velocity equals the b vector plus the a vector. But again, because the a vector is going in the opposite direction, we can say plus. It is the same thing as saying negative a with the arrow going in the same direction as b. When we plug in all of our numbers, we have 40 meters per second for b, and we have 10 meters per second for scenario A. Therefore, our resultant, our end velocity would then be 30 meters per second. And notice that it is positive, so we know that it is going in the same direction, which is to the right, that it is initially going. Here's another example of subtracting vectors, but it is subtracting vectors in 2 dimensions. So in this scenario, scenario A, the car is going to the right 10 meters per second and then going down 40 meters per second. Again, when we're writing the vector equation, we know that the final minus the initial is the velocity, and that is going to be your vector B with the arrow going down minus vector A, which is going to the right. But again, remember, that just means that you're adding the arrow going in the opposite direction. The next step is to draw the diagram from tail to end. So here we have the scenario B vector touching the tail of the A vector. Step 3 is to draw the resultant, which is right here, and that resultant will be our change in velocity. The last step is just to solve. So remember that 40 meters per second is the value for this vector. We have 10 meters per second, the value for your A vector, and all you have to do is solve. And when you solve for this, you get r squared equals 40 squared plus 10 squared, and then when you solve it all down, you should get 41.23 meters per second. Now, when you're resolving vectors, remember that this is a process of finding the horizontal and vertical components of a single vector. So for example, we have B and A vectors create this resultant. So if that's the case, then we know that every resultant vector has a horizontal and a vertical component. You can just draw those lines out and you can figure out what the vertical component value is as well as the horizontal component's value. You will need to know how to do this. So go ahead and pause the video and try to do this and then start it back up when you want to check your answers. Okay, so the first step in doing this is knowing what you are working with. So let's draw a vector diagram. So if we're using this person here as our image in order to make our vector diagram, we are given the information that her skates, the ice applies a force on the blades of her skates at 1,059 newtons at an angle of 42 degrees. So we know that the angle of 42 degrees to that of the ice is right here. So this angle is the resultant. And what we want to try to find is this vector here, which is f sub h for horizontal. And then we also have a vertical vector. The next part is to find these components. Okay, so in order to find the vertical component, we know that f sub v, which is the vertical vector, is equivalent to 1,059 sine of 42. Because if you had sine of 42, that would be opposite over hypotenuse. So that would be f sub v over 1059. And then when you move things around to solve for the vector, it would be this equation here. When you solve for this, you get 708.61 newtons, which should be filtered down to 3 significant figures. So your answer should be 709 newtons for this vector here. In order to find the horizontal, we know we would use the same angle here, but this would require us to use cosine. So cosine of 42 degrees equals f sub h divided by 1,059 newtons. When we solve for F sub h, we would get this equation here, and we would get an answer of 787 newtons, which is 3 significant figures. Here is another example, and I would like for you again to pause the video and try to do this on your own before starting the video back up to see the answer. Here we have an example of Joel weighing 284 newtons. He bodyboards down a sand dune at an angle of 23 degrees to the horizontal. The surface provides a frictional force of 75 newtons up the slope. By considering all the forces acting on the bodyboard, calculate the resultant force down the plane. Okay, so when we draw the vector diagram, we see that gravity goes straight down, and we know that that is 284 newtons because that is the weight of Joel. The friction is going parallel with that of the surface of the sand, which is 75 newtons. All right, so the next thing that we want to do is just to draw the vectors without the body, so then that way we can actually see what's going on. So here again we have the center of Joel is right here, and we have the force of gravity and the force of friction. Now, here are some other things that we know. We can draw the support force, or the normal force, which is perpendicular to that of the plane that Joel is sliding on. And in the opposite direction, we know that this is the perpendicular force, and this would be our parallel component. So it is parallel because it is parallel to the surface, and this is the perpendicular, and then this would be our resultant. So we have our two components that we're trying to resolve. Now we go ahead and push out these lines because then we can use trigonometry in order to solve for various things. And we know that this line is parallel with the perpendicular vector, and the parallel vector is parallel with this line right here. So now let's find the components. The parallel component here we have as 23 degrees, and that is sine of 23 is equivalent to the vector, the parallel vector, divided by 284 newtons, because that is the magnitude of this vector. When you solve for the parallel force, you should get 110.97 newtons. For the perpendicular vector, we're going to use cosine, so cosine of 23 is the perpendicular vector divided by 284, so you should get an answer of 261.41 newtons. Now, in order to find the resultant force, you know that the resultant force is the perpendicular and the parallel added together. If we know that this arrow here, which has it's the force of friction as 75 newtons, that is equivalent to this part right here. It is the same as this force right here. So we would then just subtract it because they are going in different directions. So we have 110.97 plus minus 75 newtons. And so your total resultant force is 35.97 newtons down the sand. Or what we would want to do is to round it off to 2 sig figs, and that would be 36 newtons down the plane. All right, this is the end of our TNOTES. Thank you very much for watching. Be sure you understand this information and can start to use it in class next.